Hello everyone. To help you prepare for the upcoming exam, in this video and the next one, I'm going to go over the study guide question by question. Although I'm going to skip some of the more obvious questions and focus more on the calculations. So you can download the study guide by going to Files, and then go to Study Guide for Exams. And you can find all the materials that can help you prepare for the exam. Download the formula sheet, also print it because you need it for the exam. For the study guide, you have study guide and also another version with the answer key. So when you practice, you can just use the study guide. And you also have the study note, which is a summary of all the concepts that we covered in the class. Now in this video, we're only going to go over question 1 through question 13. So these are all for chapter 3. And in the next video, I'm going to go over the rest of the questions, which are related to question chapter 4. Okay, so first question is pretty obvious, so I'm going to skip. But the second one is asking you to balance this following equation. This is one of the more tricky ones. So let me just show you how to do this. Okay, I'm going to write down this equation again without the physical states because we don't need those for balancing the equations. Okay, as we said in the class, first thing you need to do is to find the element that only exists in one of the reactants or one of the products. So we can start with either nitrogen or hydrogen. So let's start with nitrogen. We have one nitrogen on the left and one on the right. Therefore, it's balanced. We don't need to do anything. And next one, we move on to hydrogen. After we balance hydrogen, and then we move on to oxygen. So for hydrogen, there are 3 on the left. And then we move to the right to the products, there are 2 hydrogens. Therefore, to balance this, we can use the fractionals. We put 3/2 here, and now we have 3 hydrogens on the right. Okay, and then we move on to oxygen. Oxygen on the left, we have 2. Let's see how many now we have on the right. We have 2 here and 3/2 in water. So overall in the products, we have 2 plus 3 divided by 2, and this is 2, and numerator, we have 4 plus 3, and that equals 7/2. So this is the total number of oxygen on the right. And we only have 2 on the left, right? Now, in order to balance this, it's easier to change the coefficient for oxygen than changing it for this 2, right? So now, in order for this reactant oxygen to have a total number of 7/2 oxygen, here we divide 7/2 by 2 because there are 2 oxygen atoms in an oxygen molecule. So 7/2 divided by 2 is 7/4. So if you calculate this, there are 7/2 total number of oxygens in the reactant now. Okay. Now, we have already balanced all the elements, but they are in the fractionals. We need to find the smallest whole number ratios. To do this, we have 4 here, we have 2 here, right? And so we multiply 4 for all of these molecules, and then we get 4 ammonia, 7 oxygen. They react to form 4 nitrogen dioxide plus 3 water. is actually 6 water here. So this times 4, 3/2 times 4, we get 6 water. 6 water molecules. And then we double check each element one more time. So there are 4 nitrogen, 12 hydrogen, and 14 oxygen. Let's see the products. 4 nitrogen and hydrogen, we have 2 times 6, 12 hydrogen, and oxygen, we have 8 here and 6 here. So 8 plus 6, that's 14. So we have 14 oxygen. And now this equation is balanced. And the coefficients are 4, 7, 4, 6. So the answer is B. Okay, so before I start on each question, it's better for you to try to do it on your own, and then you will find out what your questions are. And then you restart this video again. And I think this way would help you more efficiently take full advantage of this study get questions for practice and identify which part you're lacking and which part you are pretty good, right? So that is just a little tip. Question number 3, predict the product in the combination reaction below. Well, by now you should know that, okay, first of all, this is a combination reaction. So you form only one product. And the formulation of the product, since it's an ionic compound, you have a metal, you have a non-metal combined, and the formula is determined by the common charges of the metal and non-metal. For aluminum, its common charge is 3+. For nitrogen, common charge is 3-. And therefore, the product will be this. Question number 4 is calculating formula weight. I saw that you all did pretty well for the homework and in-class quizzes. So we are just going to skip this. Question number 5 is to calculate the mass percent of carbon in methane. Methane is CH4. Okay, so this is kind of derived. It's derived from calculating the formula weight, but you have to do one more step to calculate the mass percentage. Now, to do this, you need to find out the formula weight. The mass percentage equals the formula weight for carbon divided by the formula weight for CH4, right? So you have known how to find out their molecular weight, formula weight, and just use this equation to find out their the mass percent of carbon. Now here, you can also use molar mass because molar mass and formula weight, they are numerically equal. It's just the unit is different. So here, formula weight for carbon, and then you go to your periodic table. That's why I said you need to print this out. You go to this periodic table in this formula sheet, and you find out, okay, for carbon, where is carbon? Carbon is in the second row, and you find its atomic weight on the bottom of that symbol, right? And here, you look at the answer, they all have 4 significant figures. So during this calculation, I'm actually going to keep one more. I'm going to keep 5 sig figs. 12.011 and atomic mass unit. So this is a formula weight just for carbon. And then I calculate for CH4, and it's 1 carbon plus 4 times the atomic weight of hydrogen. You find it on a periodic table, and it's 1.0079 atomic mass unit. And then you do this calculation, and you have 12.011 atomic mass unit for carbon. And these added together, you find the formula weight is 16.043 atomic mass unit for methane. And you time it by 100%. Okay, here, time it by 100%. Also 100%, right? And then you can find out the answer. All right, now moving on to the next question. Question number 6. Okay, this is obvious. Let's just skip question number 6 and let's go to question number 7. How many molecules of methane? It's actually the same molecule. So how many molecules of CH4 are in 48.2 grams of this compound? I'm trying to, let's try a different pen. Okay, so what this is testing you about is a quite important concept in this chapter is how to convert between the grams and the molar mass and the number of molecules. So if you know, oh, this is actually a weird pen. Okay, let's go back to this one. So if you know the grams, you can find the number of moles using molar mass as a conversion factor. And the same way, if you know the number of moles and use molar mass, you can find the grams. And when you know the number of moles, you use Avogadro's number to find out the number of substances. So the substance can be atoms and can also be molecules. So it can be either one. So, and also if you know the number of substances, you use the Avogadro's number, you can also find out how many moles there are in this number of substances. And from number of moles, you find the grams, you find the weight, right? So for this question, what is given is the grams from grams. And to find out how many molecules, the number of molecules. So we first from grams, we need to find number of moles. And from number of moles, we find the number of molecules, right? So let's just do them step by step instead of course, you can do everything in just one step after you are more familiar with this conversion. But now let's just do it in steps. Okay, so knowing the grams, the number of moles equals to 48.2 grams, and using the conversion factor, which is grams per mole, right? So the grams will cancel out and you will get the number of moles. Now we need to calculate the molar mass for methane. Actually, we did it in the previous question, which is 16.043, although here is a formula weight, is numerically equal to the molar mass. So the molar mass of methane is 16.043 grams per mole, which means when you have 1 mole of methane, the total mass of it is 16.043 grams. Okay, so we have for 1 mole, we have 16 point here. Because there are 3 suffixes here, during calculation, I'm going to keep 1 more. I'm going to keep 4. So it's 16.04 grams. And this entire thing comes from its molar mass. And then we get 3.005 mole. Okay, now after finding the number of moles, we can find the number of substances by multiplying it by Na, which is Avogadro's number. Again, you go to this equation sheet and you can find Avogadro number from the bottom of the middle part of it. The third column, fundamental constants, and the first one is Avogadro's number. So know where to find all the information that you need. So number of molecules is the number of moles, so number of moles times Avogadro number. So 3.005 mole times Na, and Na is 60.22 times 10 to the 23rd. And what's not reflected on the equation sheet here is the unit for Avogadro's number, which is per mole. Okay, so you multiply these two together and you're going to find out the number of molecules. And the correct answer here is D. Question number 8. Again, hit the pause, try to solve it on your own, and then come back. We'll work on it together. Question number 8, a compound that is composed of only carbon and hydrogen contains 85.7% of carbon and 14.3% of hydrogen. So these are the key information. The percentage of carbon, percentage of hydrogen, because it's a hydrocarbon, so it only contains these two elements and their weight added together should be 100%. So what is the empirical formula of the compound? Yeah, so here, given the weight percentage or percentage by mass, you're asked to find out the empirical formula. So the way we showed you to do this in the class is you write down the elements, all that, don't miss anything. Sometimes there could be 3 or even 4 different elements. Okay, carbon and hydrogen, and assume you have a total mass of 100 grams. And within that 100 grams, 85.7 grams is carbon and 14.3 grams is hydrogen. So carbon is 85.7 grams and hydrogen is 14.3 grams. Now, in order to find the empirical formula, we need to find the number ratio between carbon and hydrogen, right? And the number ratio equals their molar ratio. So what we need to do next is, based on their mass, we find the number of moles. And from the number of moles, we find out their molar ratio, which equals their smallest number ratio, right? So to do this, the same thing. Now you can see that all these questions and all these concepts are actually just interconnected together. We use the same method from grams using molar mass to find the number of moles. Here is easier because you only have one element and the molar mass is numerically equal to the atomic weight of that element, which you can find from the periodic table. So for carbon, 85.8 grams times its molar mass is 12.0. So for 1 mole of carbon, it weighs 12.0 grams. And this equals 7.14 mole. And we do the same thing for hydrogen, 14.3 grams. For 1 mole of hydrogen, it has 1.0 grams. So its molar mass is 1.0 grams per mole. And this equals simply just to 14.3 mole. Now, Step number 3 is to look at these numbers, number of moles, and see which one is smallest and divide the rest of it by the smallest number. So this is smaller, 7.14 for carbon is smaller than 14.3 for hydrogen. So we take 14.3 divided by 7.14 mole of carbon, and this equals around 2, right? So the molar ratio of hydrogen versus carbon is 2, and therefore the empirical formula has one carbon and 2 hydrogens. And here, always double check. You've already come so far and you got the ratio 2, but don't make the mistake of writing down C2H. So always double check which one has more atoms. So the correct answer here is A. Now, question number 9. A nitrogen oxide is 63.65% by mass nitrogen. The molecular formula could be done. 2 key information here. First, a nitrogen oxide, meaning that there are only 2 elements. One is nitrogen and one is oxide. And second information, it's 60.65% by mass nitrogen. So the mass percent by mass of nitrogen is given, but the one for oxygen is not. Like in the previous question, they both are given, but here only one is given. But actually you can find the other one because both of them added together should be 100%, right? So based on this information, there are only 2 elements. So knowing one, you'll be able to calculate the other one. And the rest of it would be the same. So same thing here. Write down all the elements, don't miss anyone. Assume there are a total of 100 grams. Now we know that there will be 63.65 grams of nitrogen, and the amount of oxygen can be calculated by subtracting 63.65 grams from the total weight of 100 grams. And so we find out the weight of hydrogen would be 36.35 grams. Now you know the weight of nitrogen, the weight of oxygen, and then you follow the same calculation as we showed you in this question and find out the number ratio of the 2 elements, nitrogen and oxygen. So we're not going to repeat this anymore. And the correct answer here is C and 2O. Question number 3, combustion analysis is not required, so we are going to skip this. Question 11. The combustion of propane produces carbon dioxide and water, and the balanced chemical equation is given. So the reaction of 2.5 mole of oxygen with 4.6 mole of propane will produce how many moles of water? This is similar to one of the homework questions. I'm surprised for that question, only 75% of you got it right. And this question here is actually more complicated, more difficult. So it gave you 2 pieces of information. One is you have, actually not here, you have 2.5 mole of oxygen. So 2.5 mole of oxygen. And you also have 4.6 mole of propane. You look at these numbers, then you realize they don't follow the stoichiometric ratio, right? If so, the molar ratio of this versus this should be 1 to 5. But actually now you have even more methane than oxygen. Now, based on this simple information, you can determine that, okay, oxygen is actually the limiting reagent or limiting reactant. So when calculating the number of water that can be produced, it is determined by the amount of oxygen, which is a limiting reactant, instead of the propane, right? But let's just follow the steps instead of skipping steps and see how to approach this type of questions, to first identify which is the limiting reagent, and then secondly use it to identify the amount of other molecules in the chemical equation that can be produced or will be consumed. So the homework question only involved the second step, that's why it is a little bit simpler. Okay, so let's start from the propane. So 4.6 mole of propane is given. And first let's assume that if all of these propanes are consumed, how many oxygen it will need, right? So we start 4.6 mole of propane. In order to find how many moles of oxygen it needs to consume all of these propane, what you need to do is to do this dimensional analysis based on the coefficients or stoichiometry from the balanced chemical equation, right? So based on this equation, we know 1 mole of propane will react with 5 moles of oxygen. So 1 and 5 can directly come from the coefficients in the balanced chemical equation. So now this will cancel out. You find out the number of moles for oxygen. And you do this calculation, you get 23 mole of oxygen. That is oxygen needed to react with this amount of propane, but we see there are only 2.5 moles of oxygen instead of 23. So this tells us that oxygen is the limiting reagent or limiting reactant, right? So the amount of products are determined by the limiting reactant. So we start from 2.5 mole of oxygen and find out what is it asking. It's asking for CO2 or water. It's asking for moles of water, right? So we put mole water here. This is what we are looking for. And we put mole of oxygen here so they can cancel out. And we go back to take a look at the coefficients 5, 4. So 5 mole of oxygen would react with 4 moles of water, would produce 4 moles of water. In here, oxygen cancel out, and then you get 2.5 divided by 5 times 4, and you get 2.0 mole of water. Okay, so the correct answer is D. Okay, last two questions. Question number 12. This is a question that most of you are this is the type of question most of you are still struggling with. Quantitative information from balanced chemical equations, right? It involves basically three steps of calculations, although you can do all of them in one. So calcium carbide reacts with water to produce acetylene, as shown in the unbalanced reaction below. No, you don't need to know what they are, just know they can react. So this reaction is given, and it tells you that it is unbalanced. And then how many grams of water are required to completely react with this amount of calcium carbide? Now, grams of water is what's asking, and what is given is the 82.4 grams of one of the reactant, and it's asking you, okay, like if you're running this reaction, you start with 82.4 grams of one of the reactant, and you need to determine how much water you need to add in there in order for them to completely react. So this question is a little bit difficult because it involves one step of balancing the equation. So step number 1 is to balance this equation. Start from calcium 1, 1, and then moving on to which one should we do next. Let's check carbon. Carbon is only in this and only in one of the product 2. So there are 2 carbons here, 2 carbons here, right? So carbons are fine. And how about hydrogen? Now we move on to hydrogen, 2 here, 2 here, 2 here, so 4. And then let's change this coefficient to 2, so we have 4 hydrogens everywhere. And then let's double check oxygen. 2 oxygen here, 2 oxygen, and no more oxygens anywhere else. And then I think this equation is balanced, but always double check. 1 calcium, 1 calcium, 2 carbon, 2 carbons, 4 hydrogen, 2 plus 2, that's 4, 2 oxygen, 2 oxygen. Okay, now it is balanced. And step number 2 is the main calculation in this question. So you know the grams of calcium carbide and how to find the corresponding grams of water. First you need to do is to convert the grams of silicon carbide to the moles of calcium, not silicon, calcium carbide. And like what we showed you in the previous question, if you know the moles of one of the reactant, you can determine the number of moles for the other based on the coefficients or the stock, in other words, the stoichiometry, right? So use the stoichiometry to find the moles of water. Then using the molar mass as the conversion factor to find the grams of water. In the exams, you can always write this down, write this down and follow the steps. Even you do it in one step, but writing this down can guide you through this calculation so that you don't miss anything, right? Okay, now let's just follow the steps, starting from 82.4 grams of calcium carbide. Now I'm going to convert from grams to mole. But first, we need to calculate its molar mass. For this compound, for carbon is 1440.1 plus 2 times carbon. Carbon is 12.0. So we get its molar mass is 64.1 grams per mole. Right? So for 1 mole, you have 60.1 grams. Okay, now we are here. I'm going to put check here, means this is what we have now. We have the moles. Now we have the moles of this. We need to find out the moles of this, right? By using this conversion factor. Now we just go to the equation, find out their coefficients. For water is 2, and for calcium carbide, this is C here. It is 1. Simple, right? Now this is done. We found out the mole of water. Now from the mole of water, we calculate the grams, right? So again, use the molar mass. Now this time, we need to use the molar mass for water. So we put mole here, grams here, so that the mole will cancel out. And up to here, you can always double check if you have all the conversion factors right. So here, this two cancel out, you get the moles of this calcium carbide, and then calcium carbide cancel out with calcium carbide, you have the number of moles for water. And here you have the molar mass for water. The mole will cancel out, you end up with grams of water. Now for water, the molar mass is 2 times 1.0 for hydrogen and 1 times 16.0 for oxygen. So this is just 18.0 grams per mole. This is water. So 1 mole of water, it weighs 18.0 grams. And now you just do this calculation, 82.4 divided by 64.1 times 2 and times 18.0, and you're going to get 46.3 grams. So this is the amount of water that is required for this reaction. The correct answer is C. So no matter it's given the quantities of product and ask you to find out the amount needed for the reactants or the other way around, it all follow the same, exactly the same steps, the same method for calculation. Now, if you haven't done this practice on your own, please do it on your own. Do it. We show so many examples in the class and in the homework and here. And I have also assigned quite a few after quite a few practice questions in the textbook, those end of chapter questions. So if you haven't done it on your own, please do it, because watching me doing it is different from doing it on your own. So make sure, please do it, practice it, right? Okay, last question, which is simpler. What is the maximum number of moles of SO3's sulfur trioxide that can be produced by the reaction of 2 mole of sulfur with 3 mole of oxygen? Okay, this question is slightly different. First, we need to figure out what kind of chemical reaction it is, right? So you start from, so the reactants are sulfur and oxygen. So it's basically a reaction of element sulfur plus oxygen, and that forms SO3 as a product. So what we know is that we started from 2 mole of sulfur, 3 mole of oxygen. It asking what is the maximum number of moles of the product that can be produced. So to find this out, first we need to balance the equation to find out stoichiometry, right? So 1 sulfur here, 1 sulfur here, 3 oxygen, 2 oxygen. So we need to multiply it by 3/2. Now we get also 3 oxygen on the left, and convert it to smallest whole number ratio, multiply everything by 2. So this is, now we have the balanced equation. Start from 2.0 mole of sulfur, 3.0 mole of oxygen, which actually, for the first time, that they actually is consistent with the stoichiometry ratio 2 to 3. And therefore, the product, we are going to get how many moles of SO3. So if you look at the ratio, this is sulfur versus SO3 should just be 1:1 ratio, right? So if you start from 2 mole of sulfur, you should end up with also 2.0 mole of SO3. But sometimes the ratio can be more complicated, so you also need to know how to do this dimensional analysis one more time, right? So the mole of SO3 equals the mole of sulfur, or you can also use oxygen, doesn't matter. Let's use oxygen as an example. So 3.0 mole of oxygen, just cross this out. Dimensional analysis, we need to cancel out oxygen, so I put this in the denominator, and mole of the product, SO3. Then we find out their ratio from the coefficients. 3 oxygen will react with 2 SO3, right? And so now this would cancel out. and you do the calculation, and you will end up again with 2.0 mole of SO3. So the correct answer is E. Okay, that's all for the first 13 questions. This chapter involved lots of calculation. So again, do lots of practices. Go over this and also make sure that you understand all the homework questions as well. There are 20 questions over there. Okay. If you have any questions, feel free to email me. Okay. And don't skip the next video on question 14 all the way through. I don't remember how many questions, 36, 30 something, but all the way through to the end. All right. See you.